Okay, hi, my name's Naveen. I'm going to be talking about modeling cyber physical systems, specifically in verifying models of factory floor robots. So, this research is part of the Logical Systems Lab. My faculty advisor will be Andre Platzer, and I'll also be working with Stefan Mitch, who's a systems scientist in the lab. And then some graduate students that I may work with are Young Kim Tan and Brendan Boer. Um, I've already talked with most of these people in order to get an idea of the work going on in the lab and find a project that best fits my experience. I've taken a course with Andre Platzer called Logical Foundations of Cyber Physical Systems that focuses on the logic and proofs that I'll be using in my research. So the main tool that this research relies on is differential dynamic logic. And what this is a logic that incorporates both discrete and continuous components. So in the picture, you see basically a controller that modulates acceleration, and then the accompanying differential equations that model just simple projectile motion. So the analogy you can think of is maybe a car is able to modify acceleration through braking or hitting the gas, and it's able to make discrete changes to that basically. And then the physics of the system are continuous and can be modeled by differential equations. And so DL allows you to take a model like this and prove properties about it. So for example, in this particular example, we could prove that the position is always greater than 0 if we're given that the velocity is greater than 0 in the beginning. And the main tool that you use to prove DL models is Chimera X, which is a theorem prover, and it has axioms and techniques for sequent calculus that you use to prove certain properties about the model. So the application that I will be exploring has to do with factory floor robots. So how can we model robotic arms and maybe even delivery robots? So the goal would be to prove safety properties as well as efficiency properties. So for example, proving that a delivery robot always reaches its destination without crashing into existing obstacles or stopping along the way. And then eventually we can take different models that we proved in various aspects of the factory floor, like maybe a robot for scaling a certain box onto a platform, or a delivery robot that hands off a certain package. And we basically take proofs about each of these models and put them together using component-based reasoning. So some challenges with this project. Firstly, what I mentioned about component-based proofs is a relatively new concept, and it's something that's hard to do given a bunch of models, incorporate them into one bigger one, while still retaining the safety properties you had in each. So that'll be kind of a new exploration. And then the inherent difficulty with cyber physical systems is that you want your model to be accurate about what's going on in real life, but still simple enough that you can prove properties about it. So you can imagine that proving something all the way up from first order logic in a model that actually describes reality can be pretty tough computationally. So you have to kind of maneuver this trade-off. And then in general, there are certain scenarios that are just intrinsically hard to reason about. So take, for example, a robotic arm that has a bunch of different joints. It's hard to make judgments about kind of the physics and trajectory of this arm, just given that there's so many fine, complex movements going on to create it. And the reason this work matters, firstly, is it can help improve the safety of everyone involved. So making sure that robots don't crash into people or hurt anyone in general is a very noble pursuit. And then also it can help to prevent damage to equipment and in general save money by making the factory more efficient. And then another benefit of actually rigorously modeling certain situations using differential dynamic logic is that you can discover vulnerabilities in existing systems that weren't proved using a theorem prover. So the example that I use for this is Andre Platzer contributed to work in the airborne collision avoidance system, which is basically used by the FAA to help um, prevent planes crashing into each other. And basically, by modeling this system using differential dynamic logic, they were able to pinpoint scenarios where the system wouldn't work and then propose fixes to it. So this same reasoning can be applied to the factory floor robots. If we can take existing systems and discover vulnerabilities using our theorem prover, it could be very helpful um, to preventing real-world accidents. All right, thanks so much for listening.